organizador por haberme dado la oportunidad de hacer la presentación de nuestro ponente. Así que muchas gracias. Bueno, hoy tenemos el privilegio de poder contar con la participación del profesor Javier Pérez Ramírez, viejo conocido de los mayores. Los más jóvenes le iréis conociendo con el tiempo. Bueno, el profesor Javier Pérez Ramírez es catedrático de Ingeniería Química de la Universidad de Zúrich. Y su investigación es muy variada y versa tanto en el desarrollo de nuevos materiales, incluso en el conocimiento de cómo esos materiales pueden ser modificados, pero también en el desarrollo de los procesos, con el fin de conocer qué variables podemos modificar y, por tanto, mejorar en orden de obtener, al final, procesos más sostenibles. Veréis que el amplio espectro que nos va a presentar hoy es muy interesante. Bueno, ha recibido numerosos reconocimientos. Yo me voy a centrar en dos de los dos últimos años y uno más reciente. Bueno, le han dado el premio Paul Emmett de la North American Catalysis Society en el año 2019 y el premio Robert Grasselli de SECAT en el año 2021. Y recientemente ha sido nombrado académico de la Academia de Ciencias Exactas y Naturales de España. Bueno, con esto ya nos damos una idea de que su participación, él es de Benidorm, vive fuera, pero viene mucho, incluso por Valencia, pasa por Valencia de vez en cuando. Y bueno, para la gente de Valencia es muy conocido, pero para el resto de España también. Y nada más, yo quiero agradecerle. Seguro que vamos a aprender mucho, vamos a disfrutar, porque aparte de un buen investigador, es un buen comunicador, con lo cual nos va a facilitar mucho todo lo que nos va a contar. Javier, muchas gracias.
Bueno, gracias José Manuel por la introducción. Las expectativas me las has puesto muy altas y a todos los demás. Agradecer a Luis y al comité organizador de la SECAT por tan amable invitación. Es un gran placer estar aquí con todos vosotros y gracias a todos también por venir después de una maravillosa reunión ayer por la noche todos juntos. Yo en primer lugar quiero cambiar al idioma que usamos para dar presentaciones. Quizás también en la audiencia haya alguien que no hable castellano. And I'm going to discuss with you catalysis as a driver for sustainable chemistry. And so the first is to check where everything started, the mass production of chemicals, also known as the chemical industry. It started in 1850 in Manchester, nearby Manchester, for the production of sodium carbonate. Sodium carbonate was used to make soaps, textiles, glass, etc. And already there, a few years after 1850, two gentlemen, Henry Deacon and Ferdinand Hurter, invented the first ever heterogeneously catalyzed process that was used in large-scale application. And what they did is basically to take hydrochloric acid that was the byproduct of the Leblanc process to produce sodium carbonate to oxidize it into chlorine. And they did it in 1868 over a copper chloride catalyst supported on pumice. This is the first example of heterogeneous catalysis in industry, and this is the first example of how heterogeneous catalysis was born, which is to convert a waste into a product, which was chlorine, which was sold as bleaching powder. So perhaps one of the principles of green chemistry, minimize waste. That is the origin of heterogeneous catalysis. We didn't invent it recently. However, this catalyst was very inefficient, and that's because copper chloride volatilizes under reaction conditions. So the catalyst deactivates very quickly, so this was never an industrial process that was sustainable because of the lack of stability of the catalyst. And now what happens is that during the next 150 years, there have been research and research and research in order to develop catalysts that could recycle hydrochloric acid into chlorine without any industrial success. And all the research was running around copper-based materials because copper is actually a good catalyst, but only for a very short time. And what happens is that after 150 years, we face the same problem again. In the production of polyurethanes, one of the fast-growing polymers that we have this issue where hydrochloric acid is formed as byproduct of the synthesis of diisocyanates. And we form 4 moles of hydrochloric acid per mole of MDI or TDI. So there is a very strong need, 150 years after not being successful in developing a catalytic technology, to recycle that hydrochloric acid to produce chlorine and to bring it in the front of the plant to prepare the phosgene, which is the agent to produce the isocyanates. Now, this problem has been investigated. Now there is a real need to solve this problem, right? Because you can imagine, perhaps you cannot imagine, but the cost of neutralizing this HCl is over thousands of millions of euros every year in the world in polyurethane synthesis. And not only that, the neutralization. You are losing each atom of chlorine, you are losing as hydrochloric acid. So the circular economy here is halfway. And so this was solved relatively recently, this problem. Covestro installed this plant called Deacon 2 in honor of the inventor of the reaction back in 1868 to recycle hydrochloric acid in polyurethane synthesis. And I was lucky enough to participate in the development of the catalyst. And so the plant looks like this. You have a kilometer scale. Chemical engineers, we love scales. And then we go into the reactor where we have the catalytic materials. The catalytic materials, there are 2 catalytic materials. I'm only going to focus on the top one, which is based on ruthenium oxide. Inside these millimeter pellets, you have this nice architecture of carrier, active phase, binders. I will describe them a little bit. We are in the micron range. And then where the engineering starts, it is at the atomic scale, where surfaces of ruthenium oxide, and that's the catalyst that is used, are able to architecture this reaction in a wonderful way. And as you can see, this is, of course, an animation, but you will see the reality that the catalyst contains 2 layers of ruthenium oxide. It's actually grown on tin oxide. And that's the only architecture that works for this reaction in a stable manner. That shows the singularity of catalysis. Not every ruthenium oxide on any support will work unless you are able to stabilize a bilayer of ruthenium oxide on tin oxide. Both share the same crystal structure, rutile, so epitaxial growth is allowed, forming a very stable film, which is only of 2 layers. What happens there is that hydrochloric acid splits, as you have seen in the picture. Oxygen dissociatively adsorbs. Oxygen and hydrogen, so oxygen, the HCl bond is broken. You form hydroxyl groups. 2 hydroxyl groups recombine to produce water, and 2 chlorine atoms recombine to produce molecular chlorine. Now, this image of the ruthenium oxide on tin oxide shows that this was not just a video, it's a reality. And you can see on the outermost layer of the surface of the catalyst, 2 layers of ruthenium oxide on tin oxide. And 2 and not 3. 1 layer won't work. 3 layers is a very expensive catalytic material. 1 layer doesn't work because of a strong active phase support interactions, which will render inactive catalyst. So you have to put another isolating layer in order to make 2 layers. 3 layers, you are wasting 1 layer of a very expensive metal. And that's the level of precision that you require to implement a catalytic material in this scale. The stability is great, as you can see there, 20,000 hours on the stream. And as I was mentioning before, if you put ruthenium oxide on other supports where you don't favor epitaxial growth, the catalytic activity is inferior. Most important, these materials are not stable. They're not stable under reaction conditions. There has been a lot of efforts in understanding this chemistry using a wide range of operando techniques to understand what halogen chemistry does and how to moderate or control the halogen chemistry on these catalytic surfaces. My favorite one out of the many that we develop, you imagine this is halogen chemistry, so corrosion is a big issue. Handling these reactions is not very easy. My favorite one is this one, where we use from gamma activation analysis. That's a technique that requires the use of cold neutrons. Cold neutrons are basically bombarded over the catalytic material under working conditions. They excite all the nuclei in the catalytic reactor, and then upon decay, they form gamma rays, and the gamma rays have characteristic energies, and the intensity of the elements and the intensity of these signals are proportional to the concentration. So with this technique, we could develop a correlation between activity and coverage. So this was a determination of coverage of chlorine under reaction conditions. And we could see that surfaces of ruthenium oxides are largely covered by chlorine, you know, in some cases between 88 and 100% of chlorine, already indicating that the rate limiting step of this reaction is the evacuation, the removal of chlorine from the catalytic surface. Well, this technique, it's not very common to develop techniques to measure at ambient pressure on polycrystalline materials under operating conditions coverage of a species. And when we submitted this paper for publication a long time ago, the feedback that I got from the first editor of the first journal where we submitted, which I think I showed this particularly for the young people in the audience, is that, you know, this paper is being reviewed and it's such a narrow field, you know, who cares chlorine? And your future submissions in this area need to be stopped unless you can present material of general interest. So apparently for this editor, determining coverage in catalysis, which is the dream of Lamweir, was not of general interest. So when this happens to you, young generations, don't try to downgrade your work to a worse journal. Go to a 2 times higher journal in terms of impact factor. Because editors, we make a lot of mistakes, and this is one of them. I also want to illustrate where everything started. The discovery of this catalytic material was done in Tarragona back in 2006. And the way it happened, and this is just an anecdote, I have told only this twice, the way that it happened is that my student forgot, actually, to wash the outlet products during the catalytic test. So there was actually a spill of chlorine from, through the chimney, through the ventilation system. And because we didn't have an online analyzer at that time, we did everything by titration. Actually, the person that got to know that we were forming chlorine was a neighbor from this building that was putting her clothes to dry. And so she came to the ICIQ alarm saying, something really funny is going on in your institute. And of course, I was Spanish. I had to write many safety reports. But deep inside, I was very happy because I thought, and I knew, we have found an amazing catalytic material. Because at a lab scale, you can see already a plume. You have something important. So things also start in the most ridiculous way. That's also what I wanted to say. We can frame things as we are spectacular, but things start normally like this. And these are the things that I remember at the end of the day, and I think we all remember. A catalytic material is not just a powder. It's not a beautiful spectra, right? We need to put a catalytic material to work. And these are the granules, 2-millimeter granules of the industrial catalyst. These granules contain a very unique architecture, the architecture that I mentioned before. You have 2 layers of ruthenium oxide covering tin oxide particles. This is the support. And around these particles, you have a binder to make mechanically stable bodies. And this binder is alumina. And I want to say a few words about scale-up, because scale-up is something that we don't do very often in academia, but it's extremely important because it's the translation of our knowledge into practice. And when you are trying to scale up a tin oxide powder into a real catalyst, you want to have this ideal structure. Remember tin oxide, the 2 layers of ruthenium oxide, and the alumina binder around. If you take the wrong decisions, for example, you do the logical thing of impregnating first ruthenium chloride, then you do the shaping with alumina, and then you do the hardening to make the body strong. If you really go this way, what happens, and I only show here 2 cases, what happens is that the high temperature that you do for hardening is going to sinter your ruthenium oxide. You break the layers, and then you sinter. What happens when you sinter ruthenium oxide is bad for 2 reasons. The high temperature actually transforms ruthenium oxide into ruthenium tetraoxide. Ruthenium tetraoxide is even more volatile than copper chloride. So you are losing your ruthenium. But there is even another terrible consequence, which is that when you break the layer, you leave tin oxide accessible to the HCl, and this is going to chlorinate. You produce tin tetrachloride, and tin tetrachloride is also very volatile. So all your beautiful understanding of 2 layers and coverages go to the sink because you don't know how to make a recipe that can produce tons of these materials through fundamental understanding, not just trial and error. And so the way to do it is actually to shape first and to harden, so you expose the catalyst to the high temperature before you put the ruthenium, and you only put the ruthenium at the very end. And of course, the challenge, which also cost us 2.5 years, is that once you have a tin oxide alumina body, and you impregnate ruthenium, how to guarantee that the ruthenium goes all to the tin oxide and does not split between the tin oxide and the alumina? Because every ruthenium that ends up on the surface of alumina is going to be an inactive ruthenium and will leave the tin oxide naked. And you know what happens when you leave the tin oxide naked. You are going to volatilize the support. You can notice this is probably the only slide that doesn't, in my whole presentation, that doesn't have a reference. And that is because that's the industrial property of doing scale-up. But hopefully this shows you the concept. There are many multiple additional ways to do catalyst scale-up, and it's very important, and I want to emphasize that we in academia should do more scale-up work. And this doesn't mean making grams or kilos or tons, because we are not equipped and or interested to do that, but to understand the molecular interactions that happen when you have multiphasic systems. And industrial catalysts are all multiphasic systems. The last thing I want to say is that very often we also look into the reactor at the end of the story. We develop catalyst, and then we put reactors into practice. What reactor is best for this catalyst? The reactor and the catalyst have to be developed close together from the very beginning. One has no meaning without the other, and vice versa. A good catalyst deserves a good reactor from day one. And that's what this picture illustrates. I hope you like this metaphor, that without them, they don't make any meaning. And that's why we don't say, I have a catalyst. I say, I have a catalytic process, and the process implies that you have a housing, a reactor for your catalyst that is optimal for its utilization. And so this is the pilot plant done developed and built and tested at Covestro in Brunsbüttel, where you have a cascade of 3 adiabatic reactors with intermediate heat exchange. So this first project that I illustrated just shows the best project that I've ever done with industry. And that is because the swimmers and the divers, we could live together. We are swimmers in academia. We like to explore. We like to move around. We like to exploit curiosity, even if sometimes we go outside of the problem. Industry normally has a very important target that typically has a value. And knowledge is very important, but also money is very important. And I think the equilibrium, the fact that we have freedom as swimmers, but we understand the real problem that the divers have, was the beauty in order to develop a catalytic material from very, very, very fundamental principles that now is in large scale and is recycling chlorine after 150 years of Deacon's first attempt. I wish all projects will be like this. Now, other project I want to emphasize, and now I go more into the nanostructure of the material, my favorite topic perhaps. I was talking about a bilayer of ruthenium oxide. And so let's look a little bit into other nanostructure materials. So we have this problem of using mercury to produce vinyl chloride. This is mostly practiced in China. 35% of the world PVC capacity is running using mercury chloride as catalytic material. Mercury chloride is not a very sustainable material, so there has been many efforts to find more sustainable analogs. And already a long time ago, Sinoda and Grant Hutchins has done a great job with Johnson Matthey in his reaction, amazing work. They found this correlation which basically relates the productivity of the catalyst, moles of acetylene converted per mole of metal and minute, as a function of a descriptor. And this descriptor is a standard electrode potential. So when you look at this graph, which shows like a linear trend, you know, linear trends are very dangerous. And I'm going to, this case study indicates that linear trends are very dangerous. Because linear trends make that some of these metals, like gold on top of it, have been very much studied because they are on top of this line. And other metals, like platinum, have been neglected. And you can even question whether platinum is in the correlation line, right? But okay, it's fine. So metals are neglected, they are ostracized, right? And so the question I have, or we could have, is, but what is the metal speciation in these metals? Are these metals nanoparticles? Are these metals clusters? Are these metals single atoms? Is there any relation between the nanostructure and the activity of these metals? Because the standard electrode potential is a bulk descriptor, so it has zero sensitivity to the nanostructure of the material. And you know, that's a typical view of a supported catalyst, right? You have you have a nanoparticle, this is a gold nanoparticle, you have clusters, and you have atoms. And normally you have these mixed speciations. And so one could say, and this is a joke, that a supported catalyst could be described as a supported catalyst because there is a zoo of a species in the catalyst. And if you have a zoo of a species in the catalyst, it's very legitimate to ask the question, who is doing what? What is the active species, right? And so what we did here was to find recipes, and I owe this to a wonderful PhD student I had from Germany, Selina Kaiser, to develop recipes to produce all these metals on carbon-based supports, because carbon-based supports are the materials to produce, are the best supports for these catalytic materials, to produce metals in single atom way, single atom form, ligated to chlorine, or as oxidic nanoparticles, or as metallic nanoparticles, or as naked single atoms stabilized on the carbon carrier. And what we could see is actually that this correlation that was found between the electrode potential and the conversion, actually there is no correlation. Because it's very sensitive to the nanostructure. Ruthenium nanoparticles are amazing materials. Ruthenium single atoms are terrible materials. The same goes for iridium. On the other hand, gold single atoms are wonderful catalysts, but not the same for gold nanoparticles. So what happens is that the correlation line actually is the box of the graph. There is no correlation. And that means that the electrode potential is a wrong descriptor. A better descriptor to do this is the adsorption energy of acetylene. So we have been working a lot because that is sensitive to the nanostructure. So what we could see is there is a Vulcano plot dependency where the optimal adsorption energy of acetylene is for ruthenium and rhodium nanoparticles and gold single atoms. And what you see on the edges is that these single atoms have a very strong chlorine affinity. If you have a very strong chlorine affinity, there will be no vinyl chloride formation. And on the other hand, on the left, you have nanoparticles of platinum and palladium that are strongly absorbing acetylene, so they are poisoned by the acetylene, so they are inactive too. But these correlations, which offer a new descriptor to design catalytic materials for acetylene hydrochlorination, are also not very relevant. Again, for the sake of what I said before, are these materials stable? Because all these correlations are derived for initial turnover frequency, few minutes on a stream, right? But you would like to know if these survive hours on a stream or thousands of hours on a stream, right? And indeed, what happens is that most of these nanostructures are not stable. So these beautiful rhodium and ruthenium nanoparticles during reaction conditions will redisperse on the support, forming single atoms. Single atoms of these metals over-chlorinate, so the activity is set to 0, while gold has the ability, very nice ability, to actually to sinter. And if you just stabilize gold on nitrogen heteroatoms on the carbon, you will coat them. So it's very, very difficult. So you remember in the graph that platinum was ostracized. Platinum was never touched because it was always the loser in this correlation. But platinum is the only material that is stable under reaction conditions. So a metal that has not been studied because, you know, it was put in the wrong nanostructure, probably as a nanoparticle. If it's a single atom form, it's quite active, and most important, very, very, very stable. And so this is an image of a single atom of platinum after 200 hours on a stream, where you see the dots are single atoms. And very often you say, okay, well, these are platinum single atoms, the story is over. No, the story is not over. The story is just started. Because each of these dots could be a very different species. What do you have? Where do you have the platinum? Is it attached to oxygen on the carbon? In what geometry, in what cavity, or to the nitrogen heteroatom? What kind of degree of chlorination does it have in steady state conditions? And for that, you need operando techniques. Because you cannot just do ex situ characterization of used materials and try to determine the dynamics of this single atom under reaction conditions. We are quite busy on this at this moment. I'm not able to share the final results because we are still interpreting data, but our tentative assignment of the nanostructure of the platinum single atom that works is one that has 2 ligands of chlorine under reaction conditions, and it is attached to 2 oxygen functionalities of the carbon. A very specific site. Not every site is equally active, as you can imagine. And these materials are being upscaled and are put in carbon extrudates, these single atoms, to be able to run long-term tests for this reaction and find ultimately a sustainable catalyst for this reaction. But of course, that's just an intermezzo slide just to show that you can really miss, and the literature is full of things that are forgotten because they were claimed to be wrong 30 years ago, but we didn't have the tools to characterize these things that are called wrong. So the nanostructure plays a very big role. It's not the metal, it's how the metal is expressed and stabilized on the catalytic material. Now, platinum is great, but you know, if we look at the footprint of noble metals, talking about sustainability, we can see that, you know, to produce 1 kilo of a noble metal, we will produce between 20,000 and 80,000 kilos of CO2. So 1 kilo of metal produces 80 tons of CO2. And so then the question is, now we know how to nanostructure metals. Can we find more sustainable alternatives to noble metals? One step further, not mercury, because if you look at LCA indicators, and these are typical indicators coming from life cycle analysis, human health, ecosystems quality, resources, and global warming potential, we could see that the platinum technology has a much lower footprint compared to the mercury. But that's obvious, right? Mercury is extremely toxic, right? So it's better, but is this what we need to aim at if we have the possibility to do something better? Actually, if we will shift to copper-based catalyst, you will have such a footprint that is almost 0 footprint, because it's an abundant and easy to mine, low energy to mine metal, right? And so this is an attempt, a very recent paper, where we could stabilize single atoms of copper, produce very stable performance in acetylene hydrochlorination, and follow, using operando spectroscopy, the structure of this material. Good. Then I move further into single atom catalysis. And what can we use these single atoms for in another dimension or in another area of research? And this is the first catalyst that we developed in 2015. It's palladium single atom stabilized on graphitic carbon nitride, on these beautiful cavities of carbon nitride. And you can see here, very stable. So the single atom upon, let's say, operando imaging stays on the cavity, right? Despite the electron density of the microscope, so very stable. And when we saw this, I mean, we are not organic chemists, but we saw this looks a little bit like a homogeneous catalyst. Because it's a metal atom, it's just a single metal atom, stabilized by a host, which we can call here is carbon nitride, but this is like a ligand. Well, one could, if you are not a big expert, you make these assumptions, right? I'm not an organic chemist, so I said, this looks like a ligand. The platinum is connected to some nitrogen functionalities. Can we use this in organic synthesis? And we, because of similarity, so this is a single atom, and this is a phosphine, typical catalyst for many organic chemistry transformations. So we tried this in Suzuki coupling, very easy reaction, and then we found that the turnover frequency of the single atom per metal amount of metal, very well dispersed, as single atom indicates, it's about 1 order of magnitude higher compared to some of the materials that actually are commercially used in some cases. And this is another reference, which is a stabilized organometallic complex grafted on a silica. So very superior performance, very nice. And so we were investigating this further, how these cavities stabilizing these single atoms work, and we could see that this is the nitrogen, this is the number of the coordination number, so to how many nitrogens around the cavity the palladium is connected to. Typically is connected to 6, around 6, the 6 nitrogen atoms in the cavity. And during reaction you can see that it loses coordination because it attaches the different reactants, intermediates, and so on, but it moves in the cavity. So it has adaptative coordination in the cavity to lower the energy profile so that the reaction is more efficient. It never loses the whole coordination. That's why in our hands, in this reaction, this metal never leaches. It stays on the cavity. But it has enough freedom to move in the cavity to do catalysis, to be reactive. So I think this concept of adaptative coordination, we thought that this could have nice potential for replacing homogeneous catalyst in fine chemicals production, for example. And of course, how do you do that? Then, of course, if you do a life cycle analysis, you could understand what is the real potential. And the real potential is actually order of magnitude. If you move for a palladium catalyzed carbon-carbon coupling from a standard homogeneous catalyst to heterogeneous catalyst, some of these LCA indicators are improved by not 10 times, but sometimes 100 times, orders, and 1,000 times, orders of magnitude. And that is because of the much better recyclability and reusability of a metal in a solid form compared to a soluble organometallic complex. Of course, when you work with single atoms, the first question that you are faced after the talk is, yeah, but you know, what are the loadings, how stable they are? I already told you this catalyst doesn't leach. But what loading did you use? I think I mentioned the loading here. The loading is 0.6 weight%. So the loadings are low. Because if the loadings are low, it's relatively easy to stabilize single atoms in this solid host. But you know, what happens is that when you want to make a reactor, you will like to compact activity as much as possible. Otherwise, you have an infinite volume of a reactor, so we like to increase the loading, because if you increase the loading, you increase the number of active sites in the kinetic equation, and if you increase the R by increasing the number of active sites, you decrease the volume of catalyst that you need in the reactor. This is a very simple notion. So then the question is, why cannot you produce high-loaded single atoms so that we can basically pack more active sites per unit of volume of catalyst? And yeah, the issue is that if you put more than 1%, typically what happens is that these single atoms are not well stabilized on the support, so they will basically move around, they will sinter, and they will form nanoparticles. And then you defeat the purpose of the exercise, which was to stabilize a large content of metal, but in single atom form. So we solved this problem. I'm not going to describe, because of lack of time, the recipes. But we solved this problem of making what we call ultra-high density single atom catalyst. So these are catalytic materials which display isolated metal centers
where the loadings can reach as much as 23% of metal. 23% of metal. And of course, these high loadings are typically obtained on carbon support. So here is nitrogen-doped carbon, and this is polymeric carbon nitride. You see, for many different metals, you could systematically obtain very high loadings. For inorganic supports, like ceria, you could also do a decent job. In some cases, you can go up to 10%. It's a very high loading. And so then the notion that it came when we published this recipe, which is a two-step annealing process, it's very scalable. It just needs, it's a two-step impregnation, if you like, with thermal treatment in between. Nothing fancy. It can be a scale-up. And then we thought, okay, all the notion around making these materials was to increase the number of active sites, to make more single atoms, right? But then we realized that if we can architecture, and of course you need to have a host that has the binding sites to stabilize these single atoms. Otherwise, these single atoms won't be stable because they will be mobile. You need to bind these atoms onto a functionality of the carrier. And so what we thought is that, wait a second. If we have supports, hosts, with well-defined coordination sites, like what you see here, this is a polymeric carbon nitride, here, PCN. What you could do if you could now vary the loading, and I told you that you could make high loadings of these metals, what you could do is these two extreme scenarios. So on the left, you will have a low metal loading, and then on the right, you will have high metal loadings. And what you basically do is condensing, saturating all the sites that you have to put single atoms, which are this hydrogen center here, this hydrogen center here. So you keep populating the surface with the metal. In this case, it's copper. What happens when you increase the surface population, if you like, or the coverage of copper, what happens is not only that you are increasing the number of active sites, but you are inducing synergies. And that is because now the copper atoms, the metal centers, are very close for angstrom. So they could do reactions in tandem, or they could do reactions in synergy. They are not so far away to start working together, but their structure is isolated. So atomic precision, but cooperation through proximity effects. And by applying this method, we call this geminal atom catalysis, because they are kind of twin atoms nearby. So it's a Gemini-type catalyst. And so we use these materials to produce, again, organic synthesis, organic molecules. And this is an example which I don't really talk a lot because these results are unpublished, but I think this will be a little bit of a breakthrough in trying to replace homogeneous catalyst by heterogeneous single atom catalyst, because you see the proximity of these two copper atoms enables the coupling. Here you see the two coupling reactants, the coupling partner over here, that could actually shuttle when the distance is 4.07, and during the reaction mechanism, this copper atom moves from this nitrogen to this nitrogen. So it shuttles, brings them together, and makes the reaction possible. Now, we have tested this for over 190 coupling reactions, and in more than 20 of them, we exceed by far the performance of commercial homogeneous copper-based catalytic materials. So there is a possibility to have molecular precision, and as we know, in heterogeneous catalysis, and move not only from gas phase applications, but also try to do some complexity, molecular complexity using organic synthesis. Now these dimers, and they are not dimers actually because they are isolated, so these geminal atoms are not an illusion, these are real. And so this is a picture where you see the coupling of copper sites on this polymeric carbon nitride. And what are the impact? I promise sustainable in the title, right? What is the impact of moving into heterogeneous? Well, the impact is, I already mentioned for palladium, but look for copper catalyzed cross-coupling. This is the carbon footprint of producing one product of the synthesis, product number 23, using a heterogeneous geminal atom catalyst, about 6 kilos of CO2 per kilo of product, versus a homogeneous system. This is typically copper iodide that is used, about 70. And now when you do a Sankey diagram analysis, and this comes from doing LCA and then plotting this as the flows of impacts, so I think that's a tool that we are going to use very often in catalysis, as much as DFT is used and other tools that now have become almost bread and butter. What you can see is that you can trace from the product to the starting reactants and check exactly where is the burden of each technology. What step of the overall process is creating the burden? Is it the solvent? Is it the ligand? Is it one of the reactants? Is it one of the purifications? Is it one of the separations? What is it? And what you can see is the advantage of one order of magnitude lower footprint is, in this particular case, due to the large footprint. So out of the 70.3, 50.9 of the carbon footprint is due to the synthesis of the ligand that you need to do the homogeneously catalyzed reaction. The very final part, I will take only 5 minutes, if I'm allowed. It's a little bit even more planetary. And, you know, we're doing more and more often, we're coupling life cycle analysis to catalyst design. So we do catalyst design when there is a sustainability proposition to do it. And as much as possible, it should be quantified. And one framework to quantify impacts, environmental impacts, is the framework of planetary boundaries. So these are boundaries that our planet has that we should not exceed to have sustainable development. And these are these planetary boundaries, you know, climate change, ozone layer, et cetera, et cetera, et cetera. Now, what you can do is an analysis of any chemical that is produced today according to a certain route, and then check within the planetary analysis, boundary analysis, which is like a traffic light. Green is okay, yellow is we are endangered, red is we are exceeding that planetary boundary, and you can do an analysis based on the budget, planetary budgets that these chemicals have. And what we did is to take 493 chemicals available in databases or in the small amount of databases that exist for process assessment. This needs to be much more improved, but 493 we took from EcoInvent, that's a commercial database, and then check on planetary analysis level how many boundaries these chemicals will exceed or not. That means how sustainable the chemical industry is on the basis of planetary boundary analysis. And what we found is that 99.4% of all of them, for an engineer it means all of them, are unsustainable. And they all transgress at least one planetary boundary. And the planetary boundary that is transgressed more often is the climate change, CO2 emission. And that's obvious, right? As long as all these chemicals depend on fossil fuels, you're going to have a negative impact. Then you're going to go over the planetary boundary, and on that definition that I made, you will declare this chemical unsustainable. And so there are many efforts to try to bring chemicals production within planetary boundaries, and one reaction that is being studied widely is the production of green methanol, so taking CO2 and green hydrogen to produce methanol. And what you can do is, these are the quotas, so you see the energy imbalance, this is the climate change planetary boundary. It's in red when you are doing fossil methanol from natural gas. And what you could see, if you could produce methanol in green fashion, actually you don't only get into the green of the traffic light, but you produce Earth system credits. Actually, you are removing CO2 from air. It's not carbon neutral, it's carbon negative, right? So that's very attractive. And so this can be computed, quantified in different scenarios, et cetera, et cetera, et cetera. With this effort, we try to, we work extensively on green methanol synthesis, so to try to transform CO2 into green methanol. And I just want to highlight a couple of things of this project. So of course, I'm a catalysis person, so I advocate for catalyst design. So I want to say something about the catalyst, but I want to go more into the practice of this, into the implementation of this. And this is a press release from 2021 where Total Energies, Sunfire, and Fraunhofer Institute made a claim in a press release that they will build a plant for green methanol in Leuna. And I also had the great luck to work with Total Energies in this project to develop the catalytic material for hydrogenating CO2. And this catalytic material is based on indium oxide, and I'm going to be a little bit fast on here. This is about using vacancies for doing catalysis. Indium oxide is reducible. You could create vacancies on this indium oxide, and on these vacancies you can activate hydrogen and CO2 and do reactions on it. I'm not going to extend myself very much, but this is a little bit how it works. You have heterolytic activation of hydrogen. It happens 3 times, so 3 moles of hydrogen activate, and then, you know, this is a cartoon of how the reaction mechanism takes place, and with the energy profile where you form CO2, methanol, and water. And of course, a real industrial catalyst, that, as I said before, is not a single crystal, is not a mono-component material. It is an architecture of many different materials, right? So here you have, it's very unique also, very singular architecture. You need to have a monoclinic zirconia as a carrier, because monoclinic zirconia carrier also stabilizes these very highly dispersed monolayers of indium oxide. Monoclinic zirconia and indium oxide do not have exact the same crystal structure, but pretty similar, so there is some kind of dislocated epitaxial growth that actually fosters the creation of these films. And that means when you have these films, the density of vacancies increase. Vacancies are the active sites, so you want to have as many as possible, as much as possible. And what you need to do, because indium oxide is quite lazy in splitting hydrogen, so we need to add a promoter to facilitate hydrogen splitting. And that promoter is palladium here, but it has to be atomic. It's good that it is atomic. If it is nanoparticle, it will catalyze the reverse water gas shift, so you will produce more CO, you will lose selectivity to methanol. And as we work in catalysis, we try to find a descriptor that correlates your performance, the space-time yield, with your property. And the property that we have here is the density of vacancies on the material, VO, which we could determine by operando electron paramagnetic resonance spectroscopy. There is a catalyst. You saw the environmental benefit of moving from gray to green, from fossil to green. But then there is this issue, right? And the issue is that in almost every case, the environment goes in the different direction than the economy. So these two E's are, boom, collapsing. Environmentally very nice, but what about the cost, right? And we're facing this for every new technology. Of course, the technologies we are comparing to have had, what, 80 years to optimize? And we're just starting, right, in some of them. But there is this very legitimate problem. And what we would like to do is to align these two E's, right? That environment and economy go hand in hand. Both of them are positive. And it's possible, actually. So this is a very recent study, which was very recently accepted, where we computed for Europe the cost of green methanol, and the cost of green ammonia, and compare it with the way of making them fossil, the way it's made that is today. So, and you can see in December 2019, making green methanol on green ammonia was a disaster for the pocket. Environmentally very nice, but a disaster for the pocket. But what happens? Well, things happen, right? We have an energy crisis. We have a war running around. The cost of natural gas has increased by a factor of 10. We're closing plants left and right all over Europe, right? And this is where the opportunity comes, because the cost of green hydrogen is actually much less sensitive to the crisis than the cost of gray methane, right? And what you can see now, for example, August 2022, fossil methanol was more expensive than green methanol. And now this is the last point we computed. And of course, we need to do a scenario, time scenario, and there are risk analysis. Well, that's what, engineers, we can do pretty well, risk analysis, to see progressions of this, how this will develop in the future. For ammonia, the differences are even more advantageous for green ammonia, right? So you see lower cost of green ammonia compared to gray ammonia. What it means is that we can lead in Europe through the circumstances that we are facing today. I think we can lead the green energy transition. And I read recently that was it 2 weeks ago or 3 weeks ago, Spain was for 7 hours or 9 hours only surviving on the basis of renewable energy, right? It's possible. So the last slide I have is just a reflection. This is how we operate as an industry. It has not, as a society. It has nothing to do with catalysis, but probably it prompts some inspiration on your side. So we are extracting 80 million tons per year of this stuff: fossil fuel, biomass, metals, waste rocks, industrial minerals, and construction minerals. This is what we call the natural capital. Basically, we are just stealing from the earth all these materials, natural capital, right? The natural capital is finite. We don't have more than what we have over here, right? And the way we operate is that in society, this is a Sankey diagram of the flows of these different goods, right? And about 93% of what we extract goes through society only once. So the degree of circularity of our society, what we recycle is mostly construction minerals. It's only 7% of the total economy, right? So with this model, I think we don't have too much of a chance to make a revolution in the way we do it. And of course, this is not only touching science, this touches much higher than science. I think it's more policy making. And so I think this is not a Congress for that, but I think it's actually the projection of science should go more into policy making, and sometimes our voices are there ignored or not heard or heard halfway. I don't know, but I think that's the problem that we have to solve. We have to increase the circularity of economy, and one way is utilizing better plastics and carbon oxides that are emitted, etc., etc. Biomass can be much better utilized. So after this kind of negative touch to describe reality, only 7%, we are 7% circular today. I want to finish with this slide. I come from Switzerland, so I cannot finish that presentation without the Swiss knife. And the Swiss knife basically indicates that we need tools in catalysis, and these tools are of very different nature, not only at the atomic level, but also at the planetary level. And we need to cover all these scales, and for that we need to work together in multidisciplinary teams because the expertises are extremely different in each of these corners. So that's what I have tried to convey to you. And the other thing that I have tried to convey to you is that the consequences of our decisions at the atomic scale, for those that love the atomic scale, and I think probably a huge part of this crowd loves the atomic scale, do not have only consequences on to which journal you publish the data, but it has consequences on the plants, it has consequences on the supply chain, and ultimately it has consequences on the planet. And that's all thanks to the fact that we can architecture atoms. So I think we have to, I don't know the English word 100%, pero tenemos que reivindicar lo que hacemos. Muchísimas gracias y agradezco a todos que hayáis estado aquí, las fuentes de financiación y mi grupo de investigación. Gracias a todos.
tiempo para un par de preguntas cortas y luego tenemos todo el día para intentar hablar con Javier.
Claro, claro.
Si tenéis alguna... Jesús.
Bueno, pues la verdad es que me quedé impresionado de la charla tan buena que nos has dado. Tengo una pregunta acerca de los catalizadores que estamos cambiando ahora del carbono fósil a otros tipos de carbonos, pues bio, circular. ¿Cómo ves desde el punto de vista catalítico ese viaje que tenemos que hacer desde el carbono que conocemos, que es el carbono de petróleo, a los nuevos fuentes de carbono, nuevos feedstocks diferentes, con otras funcionalidades, con heteroátomos, con contaminantes? ¿Cómo ves ese viaje que hay que hacer?
Con muchas curvas, lo veo, pero excitante. Y yo creo que lo importante, a menudo me pregunto si no tenemos ya la tecnología en la mano, sin hacer más ciencia, para empezar a transformar la sociedad en renovable. Y en muchos casos creo que lo tenemos. Lo que ocurre es que carecemos de modelos, en mi opinión, porque evidentemente la transición no puede ser hoy es blanco y mañana es negro o al revés, ¿no? Y entonces hay una transición que a lo mejor dura un siglo o medio siglo y no tenemos un roadmap adecuado por falta de modelos que nos indiquen en dónde tenemos que poner, en qué cesta tenemos que poner los huevos. Entonces yo creo que el viaje sería mucho más placentero si tuviésemos algún tipo de mapa donde podamos ver con una cierta certeza, y todos estos modelos tienen una gran incertidumbre a nivel localizado, no solamente a nivel global, porque cada país tiene sus políticas, de distintos escenarios para motivar esta transición. Y una vez tengamos esos escenarios, nosotros nos podemos encargar como científicos o gente que nos gusta manipular feedstocks o materiales, a qué dedicar nuestros esfuerzos. Pero yo creo que aventurar una tecnología que vaya a ser la líder es una locura, porque no va a existir. Y tener un mapa, podemos citar varias, pero todas no van a tener la misma importancia. Entonces yo creo que donde nos estamos obstaculizando es en no tener una idea clara de cuál es el roadmap.
Muchas gracias, Javier.
Bueno, si no, luego tenemos más tiempo. Antes de levantaros, sí que el comité organizador os va a dar la última información. Yo lo que sí voy a ofrecer a Javier no os levantéis, que va a contaros las últimas incidencias. Sí.
Bueno, ahora sí. No, que lo que estaba diciendo, quería decir primero agradecerle, por supuesto, a Javier que ha estado un rato con nosotros y sobre todo la charla. Creo que ha sido todo, por lo menos excitante, ¿no? Para todo y sobre todo, bueno, para mí me ha parecido excelente. Bueno, solamente decir eso. Por la cuestión de cómo nos vamos a organizar. Tendremos ahora las sesiones normalmente, tendremos un café luego intermedio después de las sesiones y a las 2 tendremos la hora de la comida, del almuerzo, que tendremos hasta las 3:30, ¿vale? O sea que podemos tener tiempo para... Tenemos el tiempo un poco malo, ¿de acuerdo? Porque ha estado lloviendo esta mañana, vosotros lo habéis sufrido esta mañana. Teníamos previsto para esta tarde a las 8 dar un paseo en barco por aquí, por la bahía de Torremolinos. ¿De acuerdo? Aquí desde el puerto de Bienal, que estaríamos ahí. Os diremos un poquito más adelante cómo está el tiempo para ver si nos permiten salir.